Time for us to do some practice with problems involving arc length and polar curves. So this involves, no surprise, more square roots. The way we get good at dealing with square roots is practice, because there's a lot of interesting things that can happen. A lot of it involves patience and looking for simplifications. So do as much practice as you can. If you're following along, you see a problem and say, whoa, that looks like fun. Pause me. Do the problem and see how you do. And if you need me, I'm there. You can unpause me and we can talk and see what happens. Well, let's begin. So our very first problem. Find the length of the curve. R equals root 5 e to the minus theta over 2, where theta goes from 0 to 2 pi. So there's a picture of what it looks like. Now, one of the things we can spot is we can say, well, how do we know what type of problem it is? There's two things that jump out. First off, length. So you notice a problem that involves length. But also, when we look at this expression, it's an expression which involves r and theta. That tells us we're in polar. So that's how we know, aha, we're doing our polar length problem. Now, how does it work? Well, if you have r equals f of theta, what you can say is that length is the adding up, start to finish, of the square root of your f of theta squared, f prime of theta squared, d theta. That's it. That's the formula. So, what's going to happen in our case? Well, in our case, we can say that's going to be integral 0 to 2 pi square root of, and now we start taking our derivatives, right? Well, first off, there's a function, so that'll be square root of 5 e to the minus theta over 2 squared, plus, take the derivative. Well, when you take the derivative, minus a half comes down. So minus square root of 5 over 2, and then it'll be e to the minus theta over 2 squared d theta. All right, well, what do we have? 0 to 2 pi, we'll have, here we'll get 5 e to the minus theta, and here, of course, when you square the negative, it's going to be positive. So we're going to get 5 fourths e to the minus theta. Now you can combine these, because 5 is the same as 20 fourths. You have 5 fourths, and so this becomes 0 to 2 pi square root 25 fourths e to the minus theta d theta. Ah, beautiful simplification. So we have 0 to 2 pi, 5 halves, e to the minus theta half. Okay, well, that'll be 5 halves, then e to the minus theta halves. But now we have to say, look, if it's just e to the theta, we'd be done, but there's that sort of minus a half up there. So we've got to somehow account for that. The way we do it is we divide by minus a half, which is the same as multiplying by negative 2. So this negative 2 is because of the negative half up in the exponent. Evaluate from 0 up to 2 pi. Well, of course, you can see the 2's cancel. So those are gone. So what do we have? Well, we have, this is 5 minus, because of the minus, plug in 2 pi over 2 is going to be minus pi. And then subtract a minus e to the 0. Well, a minus e to 0 will become a minus 1, so it's really plus 1. And that's it. Now, we might want to write it so it looks like it's actually a positive number. See, e to the minus pi is smaller than 1. So 5 times 1 minus e to the minus pi. Indeed, one of the things that we should check is at the end, we should get a positive thing out. If we get a negative thing out, that's a signal something wrong has happened. Because when we talk about things like length, that's a measurement, and measurements should be positive. All right, well, good. Nice warm-up. So let's keep going. On to Our next problem, doesn't want to come. It's a little shy. It's its first time being solved. No problem. Find the length of the polar curve r equals 1 minus theta squared. Theta runs from -1 to +1. So it's this really kind of curious loop. So this angle here is -1, and this angle here is +1, and we have this sort of almost teardrop kind of shape here going out to the side. This is theta equals 0. You can see it makes sense if you look at what the curve does, right? At 1 and -1, you get 0 out, and at 0, you're going 1 out. So it does match with what the behavior should be. All right, well, let's see what the setup gives us. We know we're doing length, and it's a polar curve, so we start by saying, what's our basic formula? We're going to add up, start to finish, the square root of our function squared plus our derivative squared. Okay, well, let's see what that becomes. So we're integrating alpha to beta. Well, actually, we can say what they are, -1 to +1. Great. Square root of 1 minus theta squared, right? Because this part up here, this is our f of theta. Plus minus 2 theta, that's our derivative, squared. Well, that's our integral, -1 to 1. Let's expand that and see what we get. So when we expand the first term, we're going to get 1 minus 2 theta squared plus theta to the 4th. So that's just the first term expanded out. Plus, here, what do we get? Well, we'll get 4 theta squared. All right, hey, minus 2 theta squared plus 4 theta squared combine together nicely. So we see this is -1 to 1, square root of 1 plus 2 theta squared plus theta to the 4th. And we say, aha, we recognize that. It looks an awful lot like this. I say, well, yeah, except for the minus. Exactly, except for the minus. This came from the square, 1 minus theta squared. So this will be 1 plus theta squared. And you notice that there's a square root, and therefore we say, aha, we can get rid of the square root. The square and the square root will undo each other in this case, and we end up with the integral -1 to 1, 1 plus theta squared d theta. Beautiful. Everything's positive, so there's no worry about some weird absolute value thing happening. Now we can save ourselves a little bit of work, a little tiny bit, by saying this function has symmetry. It's an even function. It's the kind of function where you could lift it up, turn it over, put it down, and look the exact same. Since we're going from -1 to +1, by symmetry we can say, look, this is the same as doubling, going from 0 to 1. And the reason I like to do this is I really like to get 0 involved. 0 is such a pleasant number to work with. So we end up with 2. Integral here would be theta plus 1/3 theta cubed. Evaluate from 0 to 1. When you plug in 0, you get 0. Ah, what a nice number, 0. When you plug in 1, you're going to get 1 plus 1/3. That's 4/3. But remember, we doubled, so we end up with 8/3. And we're done. Beautiful. What a fun problem. And it worked out rather nicely, almost as if it was meant to be. Well, certainly some thought was put into it so that we could end up with a nice square there. All right, well, let's keep going. So we'll do another problem. Find the length of the polar curve r equals cosine cubed of 1/3 theta, where theta goes 0 to 3 pi. What? Okay, what What a curious curve. What could it look like? What could it look like? Well, we don't need to know. We just start working the problem. We know length, we know polar curve, so we know our formula. So length is adding up, start to finish, the square root of our function squared plus the derivative of our function squared, d theta. All right, well, so we begin. What's our function? Well, our function is this function, cosine cubed of a third theta. So we're going to get the square root of cosine cubed of 1/3 theta squared. It's a lot of cosines there. Well, let's hope. Fingers crossed. Let's hope something happens. Well, we keep going. The derivative. Now we got a chain rule here. So 3 comes down. Then it'll be cosine squared of 1/3 theta times the root of the inside. So that's the cosine. The root of cosine is negative sine of 1/3 theta. But our onion is not done yet. There's layers, right? There's the cube function, but there's also that factor of a third. So we have to times by the derivative of 1/3 theta, which gets us to 1/3 squared. Ah, my goodness. Boom. D theta. Now, the good news is that this 3 and this 1/3, they cancel. Oh, great. That will make things nice. Okay, 3 and a third. So now let's see what we have. Well, we have, this is our integral, 0 up to 3 pi, square root of cosine cubed squared. Well, if you cube something, then you square it, you multiply those exponents together. So that would make this cosine to the 6 of 1/3 theta. Okay, now here, we're going to get a cosine squared squared. That makes it cosine to the 4th of 1/3 theta. And then we have the minus, when you square it, goes away. The sine, when you square it, becomes sine squared 1/3 theta. All right, good. Now, from here, we say, these have things in common. So let's focus on cleaning up the inside. So, looking at this, we say they both have a bunch of cosines. So we could pull out some cosines. So cosine to the 4th, 1/3 theta. And then we'd be left with 2 cosines from the first term. And then from the second term, we got all the cosines. We have 2 sines. So cosine squared plus sine squared. And now we're like, what? Cosine squared plus sine squared? We know that. That is 1. Beautiful. And this cosine to the 4th, of course, this is really cosine squared of 1/3 theta squared. So that means that the term inside the square root is a perfect square. What a beautiful thing. Beautiful. Great. So now, where do we go? Well, so that says what we really have is the integral from 0 up to 3 pi of cosine squared of 1/3 theta d theta. Now, from here, we say, well, how do we integrate that? Well, the answer is we don't integrate this. What we do is look for a way to rewrite it. So there's lots of beautiful identities in trigonometry, and one of them is called power reduction, which helps us reduce the power. You see, if it was just cosine, life is good. Cosine squared, not so great. So we're going to use the identity to help us knock the power down. So how does it work? Well, it says the following. Cosine squared of x is 1 plus cosine 2x all over 2. For reference, we don't need it. Sine squared of x is 1 minus cosine of 2x all over 2. So there we go. And now we say perfect. We'll use our identity here. So this would become the integral from 0 to 3 pi. So we have 1 over 2. I'm going to write that as 1/2 plus 1/2 cosine of, now let's be careful here. Currently we have 1/3 theta as x. So we want to make it 2x. So it'll be cosine of 2/3 theta. All right, and now we're in pretty good shape. We have something that we can work with. So we integrate. Well, we get 1/2 theta plus 1/2. The integral of cosine, positive sine. So we have positive sine 2/3 theta. And then because of that 2/3 on the inside, we're going to multiply by the reciprocal on the outside. So we're going to multiply this by 3/2. All right, well, almost there. Evaluate from 0 up to 3 pi. When we plug in 3 pi, 1/2 times 3 pi would be 3 pi over 2. Here, 2/3 times 3 pi is 2 pi. And sine of 2 pi is 0. Plug in 0. Well, that's going to be 0. Yeah, that's no doubt about that. Sine of 0 is 0. And so, we say, aha, there's our answer. 3 pi over 2. And it worked out really cool. This is one of those things where it's so clean. You know, you look at it like, cosine cubed, that's going to be terrible. But because of the way that the function and its derivative are close enough, you can actually get it out of the square root, and then we can find an answer. What a fun problem. Great problem. All right, well, let's try another problem. So, our next one. Here we go. Find the length of the cardioid, r equals 1 minus cosine theta, where theta goes from 0 to 2 pi. Okay, so that's actually the picture. So we're really trying to find what's this length. All right, well, that should be interesting, right? So let's begin. What do? Well, we start with our generic formula, which says that our length is equal to, adding up, start to finish, 0 to 2 pi, and then it'll be the square root of our function, 1 minus cosine theta squared, plus the derivative of our function. Well, the derivative of 1 minus cosine theta will be sine of theta squared, d theta. So this is our f of theta. This is our f prime of theta. Okay, so, well, what happens here? Let's see. We have, this is integral 0 to 2 pi, square root of 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. And we say, hey, cosine squared plus sine squared, we know that. That's 1. That's great. So we can say, look, this is 0 to 2 pi, the square root of 1 plus 1 makes 2 minus 2 cosine theta, d theta. Now, where to go from here? Well, in the last problem, we actually talked about power reduction, because in that case, we said we really want to get from a square down to something that's simpler without a square, so we can integrate. In this problem, we might want to do the opposite, right? We say, boy, we'd really, really like the inside to be a square. And that would be great. And if we look at this, we say, you know, there was this little fact here. There was the sine squared of x is equal to 1 minus cosine of 2x all over 2. So that was sort of the identity we didn't use in our last problem. Watch this. If you multiply it by 4, what do you see? We say 4 sine squared of x is equal, now here, 4 over 2 makes 2, so 2 minus 2 cosine of 2x. And now we're like, what? That looks a lot like what we have here. 2 minus 2 cosine of something. Okay, well, what's the key? Well, the key here is that we're thinking of our 2x as being theta. Well, that says what? It says x is half of theta. So this x would be theta over 2. All right, great. So what do we get? We get the following. We say, because of this sort of power enlargement, okay, power reduction in reverse, we can say this is equal to the integral from 0 up to 2 pi of the square root of, and here we go, we're going to have 4 sine squared of theta over 2, d theta. Now, when we take the square root, what do we get? Well, we'll get 0 to 2 pi, and now we'll have 2 sine of theta over 2. Now, at this point, you might say, whoa, hold on, Steve. We've been hanging around you for a little too long. Are you cheating us? Are you trying to trick us here? Because this feels like you might be trying to trick us. I'm like, okay, all right. Now, why might you feel that way? Well, you could say, hey, don't you really mean this is to absolute value of sine theta over 2? And I will say, this is more correct. But of course, absolute values are kind of a mess to work with. So we say, okay, do we need the absolute value? Well, let's think about what's happening. So first off, where does theta go from? Well, it goes 0 to 2 pi. Where does half theta go from? Well, it goes 0 to pi, halfway in between. So when I look at the sine function between 0 and pi, is it always positive, or is it sort of a mix of positive and negative? The answer is it's always greater than or equal to 0. So we sort of sneaked in and we're just barely okay. If we had had any part of the sine of theta over 2 had been negative when theta goes from 0 to 2 pi, we would have had to be more careful, need to do absolute value, and check our work. But in this case, we're great. It works out. Wonderful. So we're in the home stretch, right? At least with this problem. So what do we have? Well, we integrate. The integral of sine is negative cosine and theta over 2. But we have to account for that over 2. So the way we do that is we multiply by the reciprocal. So we multiply by 2. And we're going to evaluate this from 0 up to 2 pi. Okay. Well, okay, that's really a minus 4 there. So we'll just pull that out. So plug in 2 pi. Cosine of 2 pi over 2. Cosine pi. Minus 1. Subtract cosine of 0 over 2. Well, cosine of 0 is 1. So we see, oh, okay, it's minus 4 times minus 2, giving us a final answer of 8. And that's it. It's 8. Wow, what an answer. It's not the kind of answer that we probably would have thought of when we start, because you thought, oh, well, it's kind of, it's polar. There's pi's all the time when you do stuff in polar. There's probably going to be some kind of 5 pi or something. But, no, it turned out to be this really lovely number. All right, great. Fun. Good stuff. So we should go on and try another problem, right? Of course we should. So let's do one more problem to finish this up. Okay. Set up, but do not evaluate. You probably think, what sweet words those are. Well, usually that's a sign that we don't want to be evaluating. So, set up, but do not evaluate an integral that finds the length of the Archimedean spiral, r equals theta, where theta goes from 0 to pi. In fact, this is a picture of it, so there it is. Also set up, but do not evaluate, an integral that finds the surface area that results when the Archimedean spiral is spun around the x-axis. So there's two things, one about length and one about surface area. Well, the length is pretty straightforward. So what do? Well, length, start to finish, and then it'll be the square root of your function squared plus the derivative of your function squared. Well, in our case, our function is simply theta, r equals theta. So that makes it integral 0 to pi, because that's where our bounds are, 0 to pi. And then we have the square root of theta squared, and derivative of theta is 1. 1 squared is 1, d theta. Good. Now you're probably thinking, can we integrate the square root of theta squared plus 1? There are actually ways to do it, but it's not trivial. There is trig involved. So it's a great story, which we'll get to in a different session. But they're only halfway done. That's the length of the curve. What about the surface area? Well, let's think about what we're doing. We're going around the x-axis, so we're spinning this way. And how do we do surface area? Well, for surface area, we do the following. We add up start to finish. I'll go ahead and make them angles because we're in polar. And then we're going to have 2 pi, a radius, and a length. Well, what are these pieces? Well, the way we think of it is we say, hey, what we should do is really chop the curve up into little tiny pieces. So there's a little tiny piece there. And what we want to know, the radius, is how far you are from where you spin. Now, let's answer that question first. So for us, what's the radius? Now, before we panic, let's just give an answer. Don't panic about it has to be the final answer. Just say, look, let's just give an answer that we're comfortable with, and then we'll work with it. So if we say, for instance, we're spinning around the x-axis, then the distance is y, right? That's how far you are from the x-axis. And now at this point you're saying, we can't use y. No, but it's a good stepping stone. So we know, okay, what is y for our curve? Well, in our case, we would usually think of it as r sine theta. So that's how we convert a y coordinate, between polar and Cartesian. Well, in our case, we know we're on the curve r equals theta, so we have theta sine theta. So that's our radius, theta sine theta. Our bounds, by the way, are freebies. We already know where we go from. What about length? Well, we actually know it. You see that formula we came up with, that expression, square root f of theta squared plus f prime of theta squared d theta, that's the length formula. And the thing is, it's right there. That's what we were computing. So this is the square root of theta squared plus 1 d theta. So, putting it all together, what do we get? We get the following integral. Going from 0 to pi, 2 pi theta sine theta times the square root of theta squared plus 1 d theta. And we set it up. I'm pretty confident that we should not want to integrate this one. I don't know if we could. There's a lot of integrals we can integrate. We can always find it, of course, up to very high precision. But our goal was to set it up. And we did. And you probably should say, that feels kind of similar to other things that we've done in the past, broken things into parts. As long as we remembered our basic formula, just think about what happens to every piece, it's not so bad. And that's going to be a good idea. Think about the generic formula. What do the pieces correspond to? Instead of memorizing lots of special cases and then driving yourself crazy trying to remember all those things, just memorize a half dozen generic forms and you can handle almost everything that gets thrown at you. Well, okay, that was our practice with length and polar curves. Hope you had fun. I know I did. And we'll see you again in a future session.